This is a photograph of your humble host taken earlier this summer at the Anchorage Museum. This is a 12 megapixel image. If you load it in NumPy, you'd find that here we have 3,000 horizontal pixels and 4,000 vertical pixels. So that's 12 megapixels. And then we have 3 color channels. So overall, we have 36 million pixels. Each is stored in 1 byte. So we have a value between 0 and 255. So it's 36 megabytes. But on my computer, this file only takes up 3 megabytes. That's because the image is JPEG compressed. We'll talk about the JPEG algorithm in Chapter 7. The camera that took the picture actually has 100 million photocells. The 100 million pixel image is processed and compressed to turn the image into this JPEG file. There's a certain divide going on here. We have all these photosites. So here's our detectors. And then that's read out electronically, goes into digital processing. So here's our digital processor, and that turns it into a digital file that we read out here. Now, in computational imaging, we want to break down these barriers. We want to make the system as powerful and as efficient as possible. So we're stuck with the question, why did we make 100 million measurements for this 12 megapixel image that we're going to represent then with 3 megapixels? Well, we could find ways to turn this sampling into something that we have a analog digital processor here that's going to do more interesting sampling and could allow us to detect more data. Earlier I talked about how the power of this sampling process is the primary limit on information. So we can make that more efficient, but then we need an algorithm other than just saying here's our pixels to represent the image. This algorithm has been the basis of what's known as compressed sensing. In compressed sensing, we try to make the sampling more efficient. The workhorse algorithm for estimating the image from compressed sensing has been what's called the Lasso algorithm, which is what we'll talk about today. Computational Imaging. Episode 15, Lasso Regression. Episode 14 discussed Tikhonov regularization, where we tried to minimize the regression error plus a power constraint, the energy constraint that limits the L2 norm of the signal. Lasso regression instead chooses to minimize the regression error plus a L1 constraint. This would be forcing the signal to have as few coefficients as possible, which makes the signal sparse. Lasso stands for least absolute shrinkage and selection operator, and the goal is to minimize the magnitude of the coefficients of the signal. We won't get into the details here, but it's provable that under appropriate sampling conditions, this L1 constraint will achieve a decompressive inference, that if for signals that are suitably random over the object space with suitably randomized measurement systems, this will achieve the true signal with high accuracy. The problem with Lasso regression is that, in contrast with Tikhonov regularization, where we had an algebraic solution for the Tikhonov estimated signal, with Lasso regularization, there's no algebraic way for us to solve this problem of minimizing the estimated signal against the L1 norm. So instead we use convex optimization. So convex optimization uses a gradient descent. This over in B here, this is non-convex optimization. We have a estimated signal. We try to change the signal estimates to reduce the regression error and the L1 constraint. If it was a non-convex system, you would get caught in a local minimum. But if it's a convex system, this gradient descent approach will yield a true local minimum, which will be our best estimated signal. So we won't get into the details of convex optimization algorithms. We live in this magical world where if we want to do Lasso regularization, we can just go to sklearn, a library in Python, and use the linear model.lasso with an appropriate minimization constraint, minimization parameter, and fit a model to solve the Lasso problem. So if we look at the random sampling that we did in the last lecture, we see that with the noisy system, Tikhonov regularization produces a noisy signal, whereas the Lasso estimate is very close to the true signal. Now here we're using these atomic spectra. So the atomic spectrum here, we have 1,024 signal components and maybe less than well under 100 signal lines. So this is what's a very sparse signal. Lasso will converge to it tries to minimize the number of parameters we're using to estimate the signal using this L1 norm. So it will converge to a sparse solution to the signal. Now, the problem we have, of course, if we're trying to build computational imaging systems, is that images tend not to be sparse. The images are distributed and have non-zero values everywhere. We've seen, however, that images are sparse on a wavelet basis. So if we do lasso regression on a wavelet basis or choose a basis for the signal on which it's sparse, lasso regression is likely to find the true signal. A simple way to do this is to note that many images are sparse in their derivatives. So instead of minimizing the L1 norm for the image, we could minimize the L1 norm for the gradient of the image. This is called total variation regression. And so the constraint becomes that we're going to minimize the regression error plus the total variation. Now, actually, you could choose any of a wide variety of different potential optimization functions. This is called a prior, right? That we're trying to match the regression plus some prior. So there's a diversity of algorithms that could use different algorithms or different priors. Total variation emerged in the early 1990s and has been used for a very long time to do denoising on images. So here's an example of that. We have an image with random salt and pepper noise added to the image, and the total variation restored image takes out that kind of high variations. And so the underlying idea here is that noise tends to have a high derivative, so the noise tends to vary quite a little. So if we try to minimize the derivative, we would reduce the noise. What that does, of course, is smooth the image. So here in the detail of the total variation image, you see that the image has been substantially smoothed in the process of doing noise reduction. So compressive measurement, which we talked about in the introduction to today's discussion, became very popular from 2004 on, and was used to build a wide variety of systems. And this total variation algorithm was used as the inverse solution for many compressive measurement systems. So in compressive measurement, one has the freedom to change the forward model to optimize against some constraints on system performance, and then try to use a decompressive inference system to estimate the signal. Here's an example of this using something called coded aperture snapshot spectral imaging. We'll discuss this in chapter 4. You see on the right these coded data that's measured from these burning candles, and on the left is an RGB color video of the scene. Now, if we take this compressed data on the right, the coded data, and use a total variation regression process to reconstruct the hyperspectral image, one can recover this data from the coded data. Here, you can see the bodies of the candles are lit up at the three spectral lines corresponding to the neon lights, and the flames are lit up at some lines corresponding to chemical reconstructions. You see that so this is powerful. From those single coded frames on the previous slide, this entire hyperspectral video was reconstructed. But obviously, this is not super high quality images. Here's a more recent example from Xin Yuan's group at Westlake University, reconstructing data from the coded data on the upper left. The upper right image is using total variation, a particular algorithm for implementing total variation where you get a 26 dB reconstruction signal to noise, peak signal to noise ratio. But at the lower right, the same data is reconstructed with a feed-forward neural network. So, I've explained to you today this lasso algorithm and total variation. They're useful as processors in this inverse problem, but they have been largely overtaken by neural processing, and so we'll need to understand how to do neural processing to understand the current state of computational imaging, and we'll do that right after the next lecture.